Hey guys, welcome to question 3 for the 2013 mechanics paper. So this is momentum and energy, and we'll just get into it. Each bumper car has a rubber bumper all around it. The mass of a bumper car is 240 kilograms. Jason has a mass of 65 kilograms and is traveling at a speed of 2.4 meters per second. Calculate the size of the momentum of Jason and his bumper car. Okay, so you know that the mass of the bumper car is 240 and the mass of Jason is 65. So total mass of the car plus Jason would just be 240 plus 65, and that's going to give us 305 kilograms. And then we also know that momentum equals to mass times velocity, and then it tells us the velocity is 2.4 meters per second. So we will just say 305 times 2.4 equals to, plug into our calculator and see what we get. So we're going to say 305 multiplied by 2.4, that gives us 732 kilogram meters per second, which is the unit for momentum. Always remember the unit. Okay, for this question, it's just an achieved question. It's not too much drama, so just achieved. Okay. The bumper cars are designed to minimize injury. Discuss the reasons for the bumper cars having rubber bumpers all around them. Assume cars with and without bumpers have the same mass. Assume change in velocity is the same with and without bumpers. Okay. So basically, as you can see here, it says assume cars have the same mass and the change in velocity is the same. So like we know that P equals to mv, right? So we know P equals to mv. And because the mass is constant and the velocity doesn't change, that means the momentum doesn't change either, okay? So it's important to note that down. So because the mass is the same and the velocity is the same, that means the momentum is going to be the same because P equals to mv. Okay, so when a car has a rubber bumper, that means its rubber bumper is soft. It's more able to be compressed, compressed due to a force. So, for example, Jason has a collision with another object. So during the collision, the rubber bumper is going to compress, and then this actually increases the stopping time of the bumper car. And because it increases the stopping time, that actually means that the force experienced by Jason is going to go down, because we know that the impulse equation, so change of momentum equals to force times change in time, and because change in time has increased, that actually means that the force experienced by Jason has decreased. Okay. So just to write this down in a paragraph form. So basically, we're gonna start not duplicate, sorry. Okay, so basically we're gonna start off our answer by saying, because the mass and the velocity is the same, and P, no, not capital P, it's lowercase p. Okay, so P equals to mv. This means that the change in momentum is the same for any bumper car. It's the same because we assume that the mass and velocity is the same. That's the only reason. Okay. When we have bumper, not rubber number, rubber bumper, the rubber is a soft. So we say the rubber is a soft material, and therefore it can compress during a collision, and hence it will increase the stopping time. Okay, because since it's compressed, that means each second there's less change in momentum. Okay, so that means after more time, the same change in momentum will happen. Okay, so basically that's what I'm trying to say. So basically, like because change in momentum equals to 4 times change in time. Basically, force equals to change in momentum divided by change in time, and because change in time increases, we decrease the force, okay? So basically less change in momentum per second. And this hence increases the stopping time of the card, okay? Increase stopping of time of the card because change in P equals to F times change in time, and the change in time has increased. Therefore, because the change in momentum is constant, we can say that the force experienced by Jason and the car will decrease, okay? And it decreases because there's a higher stopping time, okay? That's basically it. Okay, so that's your final answer, really. And that should get you answer to excellent. So it says on the marking schedule, so you have to mention that rubber bumpers reduce the force. Okay, so by adding in a rubber bumper, it reduces the force experienced by Jason. You have to state that the rubber compresses to increase the time of the impact. So we stated here that the rubber is a soft material, so therefore it can compress during a collision, and this actually increases stopping time. So we said that. And then we'll also say, since change in momentum is the same. So we said that the mass and velocity is the same, and P equals to mv, therefore the change in momentum is the same. And therefore we can say that the force is actually determined by, the force experience is determined by how high the time is, okay? Alright, so basically this should be an excellent answer here. So just say this should be. We stated all three of these points, okay? So to get merit, you basically just say state two of these points. So we say, so the 3 points I mentioned in the excellence, you only need to state 2 of them to get merit, and you only need to state 1 of them to get unachieved, okay? But most of you should be aiming for the merit and the excellence grades. So you have to be linking the same momentum to the formulas as well in order to secure your excellence grade, okay? You never know what the marker is going to be like. You're going to have sometimes more pedantic markers. They're going to look for more precision in your work, okay? Just make sure you include the extra detail so they have no excuse to mark you down. Alright, next one. Jason collides head-on with Janet, who is in another bumper car. The bumpers don't work properly, and after the collision, both cars lock together. Very important to note down that the cars lock together, because that means that the masses are combined, okay? The mass of each bumper car is 240 kilograms. Jason has a mass of 65 kilograms, and Janet has a mass of 58 kilograms. They are traveling towards each other in opposite directions. Jason with a speed of 2.4 meters per second to the right, and Janet with a speed of 2.7 meters per second to the left. Calculate their combined velocity after the collision. Include a direction with your answer. Okay, so basically in this question we're just going to say we're assuming conservation of momentum, so the initial momentum is equal to a final momentum, okay? So we're just going to say, to start it off, we're just going to say P equals to mv, okay? So we're going to calculate Jason's momentum. Jason is 65 times 2.4, acting in the right direction. That not 65, it's, I did it, it's 240 plus 65, sorry, so 240 plus 65 whole times by 2.4, acting in this direction. That gives us that should give us 732 kg acting in the right direction, okay? So now I figured out the Jason's momentum, and that's 732 kilogram meters per second to the right, okay? So now we're gonna try to figure out Janet's momentum. So that means I'm gonna say 58 times 2.7. Well, not 58. Well, I did it again. Sorry, I did it again. Oh my god. So 58 plus 240, that's 298, going to say 298 times 2.7. Let's say times 2.7. That equals to so 2.7 acting in this direction. We're going to say 804.6 kgms minus 1 is acting in the left direction, okay? So now we're going to use vector addition to find out the initial momentum, okay? And once we found out the initial momentum, we're going to equate it to the final momentum, so P initial equals to P final. And then we're going to find out the final combined velocity, okay? So remember when we say combined velocity, that means they're traveling together, and therefore we have to add their masses together, okay? So basically we're going to say 372 acting in this direction plus 804.6 acting in the opposite direction, okay? Okay, so basically because they're acting in opposite directions, we're not going to add, we're going to subtract because they're acting in opposite directions. So we're going to say 732 minus 804.6, and that gives us 732 minus 804.6, that equals to negative 72.6 kg ms minus 1 acting in the right. Okay, so we know that we can't have a negative momentum, okay? It's impossible to have a negative mass, and it's impossible to have a negative speed, okay? It doesn't work, okay? So basically we're gonna flip the sign and we're gonna flip the direction, okay? So remember, when you have a negative, flip the sign, flip direction, okay? You have to do both. So instead of negative 72.6 acting to the right, we're gonna say it's positive 72.6 acting to the left, okay? So we're going to flip the direction, okay? So now that we figured out our initial momentum, we're going to say Pi equals to P final, okay? Okay, so we're just going to find some more space at the back of the book. Okay, there's no space at the back of the book. That's great. We're going to we're just going to do it here, okay? Forgive me, okay? So I'm going to say initial momentum is equal to final momentum. We know the initial is 72.6 acting to this way equals to. So basically they're moving together, right? So like I just said, if they're moving together, we have to have a combined mass. So Janet is 298 kilograms, and Jason and the car is 305 kilograms. If we add that together, we get 603. So 72.6 acting in the left direction equals to 603. You know that P equals to mv, so it's a mass times an unknown velocity, okay? So to find the velocity, we're just going to move the 603 to the other side of the equation. So we're going to say 72.6 divided by 603, okay? So we move with dividing now, since if we multiply on one side, we're going to divide on the other, okay? So if we find out, we get 0.12, and when we divide, we just keep the direction, so it's still acting to the left, and that equals to the velocity, okay? So therefore, you can rewrite this as v equals to 0.12 meters per second, and remember to include the direction, so it's in the left direction, okay? So there we go. I think that should be our final answer. Yep, that's the final answer. So 0.12 meters per second acting to the left, and that all the working and the final answer gets you the excellence grade. To get to a merit grade, okay, so you just basically, you're getting up to here. You're saying that the 72.6 to acting to 72.6 kilogram meters per second acting to the left is equal to 603 kilograms times velocity, okay? So if you're getting up to here, when you haven't solved the final answer, you'll get a merit grade, so this will get you merit, okay? And if you want an achieved grade, if you're getting achieved grade, it's basically just getting to this first step here. So this first step completed, finding out the momentums, but not adding or subtracting them is just achieved, okay? Basic, okay? So obviously going to be trying to aim for the excellence mark here, okay? And that means you have to with the final answer and all the working. Okay, so hopefully you understand what I just said in that question. Okay, comment down below if you don't. Okay, don't be afraid to comment. Okay. The rubber bumpers in Jason's bumper car has a spring constant of 78,000 newtons per meter. On one occasion, he collides with the wall, causing a compression of 15 centimeters. Calculate the elastic potential energy stored in the rubber bumper. Okay, so this question will just simply say that EP for elastic potential energy equals to half kx squared. So in this equation, in this question, they've already told you the spring constant, that's 78,000 newtons per meter. And they've told you the compression, that's 15 centimeters. So basically, you already know K and you already know X. So basically, we're just going to substitute these numbers in and we'll find out EP, okay? It's just as simple as that. So we're going to say EP equals to 1 over 2 multiplied by 78,000. That's the spring constant. And we multiply. So remember, it's 15 centimeters, right? In physics, we're always going to convert that to meters, okay? So it's not times 15 squared, it's times 0.15 squared, okay? So remember, we're converting to meters, okay? So 0.15 squared, okay? Plug this into our great calculator here, and then we should be getting our answer. So 0.5 times 78,000. That's a very stiff string. And we're going to times by 0.15 times by 2. And that gives us 877.5 joules, okay? It's as simple as that, okay? So that is, since they've already given you, like, everything you need, and you only substitute it into an equation, that's only going to get you an achieved grade, okay? So not too much fuss. Determine the impulse if the collision lasted for 0.8 seconds. Include a unit with your answer. Okay, yeah. So in this question they're actually referring to I think. They're referring to I, not the first one, okay? Okay, so determine the impulse if the collision lasted for 0.8 seconds, okay? So you've already calculated the EP, that's 877.5 joules. Okay? And we know that Hooke's law, F equals to negative kx, okay? Or like I stated in a previous video, I think, that the negative only represents a change in direction. It doesn't represent a negative spring constant. Okay, so we can basically just ignore the negative. We can just say F equals to kx, okay? So we know that EP, so we just say EP equals to 877.5 joules, okay? And we're gonna say that f of x, oh god, getting calculusy here, okay? So F equals to kx, okay? So basically, they've already given you 78,000 newtons per meter, and they've given you the compression, 15 centimeters. So the force, okay? So basically, how you have to think about this, like, imagine you have a spring, okay? You have to apply a certain amount of force by your hand, and you gotta pull the spring in order to stretch it, okay? And you have to, so basically you're providing a certain amount of force to stretch the spring a certain amount of distance. And depending on how tight the string is, so if you have a really, really tight string, you might find that it's really hard to pull it. The reason it's hard to pull it, okay, is because it has, it's very stiff and it has an extremely high spring constant, okay? But if it's like really loose, that will make it really easy to pull, so you can apply less force and you can pull it really easily, which means it has a lower spring constant, okay? So basically what this question is saying, so when the two rubber cars collided together, there was a certain amount of force by the collision that allowed the spring to compress by a certain amount, okay? So because there was a certain amount of force during the collision, and because this certain amount of force caused the spring to compress, okay? So compress a certain amount of distance, okay? So basically we're trying to find out what the force of the collision is, and then we'll substitute into the impulse equation, okay? Okay, so basically F equals to 78,000 multiplied by 0.15. That, if you plug that into the calculator, that should give us okay, what is going on? That gives us 11,700 newtons. Okay, so the force of the collision was 11,000 newtons, and this 11,000 newtons allowed the spring to be compressed 15 centimeters. Okay, so you might be thinking, oh wow, that's a lot of force and only a really tiny compression. Well, that's because the spring is really stiff. As you can see, it's 78,000 newtons per meter. Okay, so therefore, what newtons per meter is saying? So that's basically saying that I need to exert 78,000 newtons of force in order to make the spring compress only 1 meter, okay? So if I had 1 newton per meter, that means I only have to apply a 1 newton force to make the spring stretch 1 meter. So if I had, for example, 500,000 newtons per meter, I would have to apply a force of 500,000 newtons in order to compress the string by 1 meter, okay? So basically, the higher the spring constant, the stiffer it is, and the stiffer it is, the harder it is to move, okay, basically. So we found out the force of the collision is 11,700 newtons, okay? So now we're gonna say that that the change in P, change in momentum equals to force times multiplied by change in time. Okay, so basically they've already told us the change in time, which is 0.8 seconds, and now all we have to do is plug our numbers in. Okay, so basically change in momentum equals to 11,000 times 0.8, and that should be giving us times 0.8. That gives us 9,360 kilograms meters per second. Okay, and that should be your final answer. Answer here should be 9,360 Newton kilograms meters per second. Okay, so getting all the way up to here should get you a merit grade, and getting an achieved, let's see, well, for this question, it doesn't look really like you can get an achieved. So basically, the only way you can get an achieved is by saying 9,360 without the unit. Okay, that's basically it. Okay, so yeah, that's 9,360 kilograms meters per second. Okay, that should get you a merit grade. Okay, so yeah, one thing I didn't really like about this question, so like, I thought like it's really easy to think that this question is actually referring to this question up here. So it might be referring to you would think that would be referring to this question, but remember that in this question we were assuming conservation of momentum, so the initial momentum was equal to a final momentum. So unless you're trying to find the force experienced by a certain unit, so for example, the question might ask you, what was the change in momentum for Jason, okay, or what was the change in momentum for Janet? But the change in momentum for the system in general is 0, okay, because we could assume conservation of momentum, and the initial momentum is equal to the final momentum. But the change in momentum on a single object, there could be a change in momentum on a single object in the system, okay? So the overall system experiences no change in momentum, but an object in the system during the collision would experience, could experience a change in momentum, okay? So a possible question could be asking you, so Jason was initially traveling at 2.4 meters per second, okay? And now after the collision, he's traveling at 0.12 meters per second in the opposite direction. So obviously, you can tell without any calculations, you can tell that there was a change in momentum. And for Janet, obviously, she was moving at 2.7 meters in the left direction, and now after the collision, she's only moving at 0.12 meters per second in the same direction. Okay, so obviously you can tell that 0.12 meters per second is less than 2.7 meters per second, and therefore you can tell that there's a change in momentum. Okay, but the change in momentum as a system, so the initial momentum of the entire system and the after momentum of the entire system is the same. Okay. So in this question, they didn't specify like if you wanted to find the momentum of Janet or the momentum of what was his name, or the momentum of Jason. So therefore, the question couldn't have been referring to this first question. I had to be referring to the to the first part of D. Okay. Yeah. Sorry if that was a bit confusing. Okay. But it's just something you have to remember. Okay. All right. So thanks. I think that's it. Yeah, so thanks for watching. Hope you liked the video. If there's anything you don't understand, please comment down in the comments below, and I'll explain it to you. Or if you don't want to do that, you can also DM me. My Instagram is kfudaman. You should be able to find it. It's a pretty unique Instagram ID. So you can just DM me on Instagram, ask me any questions. Nobody would know, and it's fine. Okay, I really don't mind. It could take me a little while to respond. Okay, but I will respond. Okay, if you do ask me any questions, I'll try my best to give you an answer. Okay, so thank you guys for watching this video. Hope you enjoy it, and I'll see you in the next one. All right, thank you. Bye.